Hello everyone, please let me introduce myself. My name is Amartya Natayu, and on behalf of our research group, I would like to present you about our work on a Micro Quadrotor gas source localization benchmark in a low-computational controller. A brief introduction into our research. Order seeking is a complex engineering problem that has grabbed the attention of a large number of scholars. Due to the tumultuous nature of odor distribution when combined with the atmosphere, this research subject is both complex and fascinating. Using an airborne vehicle, particularly a quadcopter, for odor source localization has various advantages, include a greater flexibility, agility, and quick search without relying on the terrestrial terrain for starting point. A micro quadcopter is used in this research to enable the investigation of narrow regions. This study proposes a novel strategy for odor source localization by addressing the payload problem by taking numerous aspects into account, such as investigating the payload limit and comparing it to works by other scholars. In achieving the odor source localization using the micro quadcopter, there are various methods applied. The first method is the program behavior of silkworm moth searching mechanism. The silkworm moth approach is one of the procedures in locating reactive odor sources. The method mimics the behavior of the silkworm moth when tracing the trails of female pheromone, which is characterized in three primary movements, which is the surge, zigzag, and loop. The surge begins when the moth traces the female pheromone, and the moth will fly towards the direction of deodorant until the pheromone fades. The moth then will zigzag until it rediscovers the female's pheromone after it has evaporated from the sensory system. However, previous research by Kanzaki et al., using a female moth as reference and moth as the control, shows a difficulty where the moth has trouble in locating the manufactured pheromone, thus making it lose track of the chemical molecule at a certain position. This finding compelled us to forsake the zigzag looping strategy in favor of the spiral movement in order to minimize the probability of losing time seeking owing to an orientation angle change. The second method will be inverse modeling. The second method is because the gas sensor will be attached to the quadcopter's body. This situation creates difficulty with data detection. The disruption was produced by the propeller's airflow, which interfered with the odor detection. To overcome this issue, an inverse sensor model is employed to determine the presence or lack of odor in the atmosphere. For the inverse model, the autoregressive with exogenous input or RX model is used. This is because the RX model may be used to explain a large number of non-class linear systems with minimal parameter. The RX model is explained in the figure. Tilde k is the estimated value of the input at the kth step, and y is the time differentiation for output sensor voltage at the kth step that has already been filtered by the Savitsky-Golay filter. Then for the A1, A2, B0, B1 is the RX model coefficient. The third method is the Savitsky-Golay filter, or SGF. SGF is a type of digital filter that can smooth and improve precision without changing the signal strength. With the linear least square method, suitable sequential subset of contiguous data points are constructed using a low degree of polynomial. It is possible to create a smooth signal estimation at the central or beginning of each data subset using a single set of convolution coefficients when the data points are equally distributed. Consider a collection point of xj and yj equal to 1 until n. Xj is the independent variable and yj is the observed value. In this investigation, as x is representing time and y representing odor information. Thus, those variables are processed using the set of MCI convolution coefficient as specified by the expression. Prior to investigating the sensor into a micro quadcopter, an individual task was performed to compare the performance of MA and SGF with direct odor detection. The result is as illustrated in these three figures, and it shows that SGF outperforms MA when the required data point for smoothing is of high order. In developing a low computational controller system, in this study, a DJI Tello is used as a micro quadcopter. To develop the low computational controller system, the microcontroller is ESP32. The ESP32 is a low-power, high-integrated MCU-based AOC that supports 2.4 GHz Wi-Fi and low-energy Bluetooth. This type of microcontroller can help to minimize an enormous burden, particularly a heavy weight, due to the many of GPU, and it operates at a low voltage. The processing for the program behavior is performed by the ESP32, with the protocol of communication between the DJI Tello and the ESP32 being Wi-Fi. To ensure the suggested approach is properly being validated, the testing area in the room is as specified in the figure. The frequency of odor stimulus is 1 spray for every 2 seconds, and the fan speed is 420 cubic feet per minute with no swing fan. Other considerations are the odor used in this research is butane, and the gas sensor is MIX 5524. The camera is also used for record and generate trajectory of the micro quadcopter after the experiment has been finished. And the purpose is to gain the behavior of the quadcopter motion. The success category is set to whenever the micro quadcopter reaches the circular red zone with a diameter of more or less 250 mm. This is a demonstration of the video of the successful attempt of the micro quadcopter when locating the gas source. The experiment has gained us various results. The experiment is done in 10 trials, and the results are used to assess the efficacy of the odor localizing algorithm developed using the proposed strategy. The tiny quadcopter can achieve a 70% success rate with the low computational controller with an average time of 24.57 seconds. Figure 1 and 2 show successful attempt in forming a search spiral state. However, the spiral is not fully created due to the odor information was received by the micro quadcopter before the spiral conditions were met. The third figure depicts a trajectory pattern for the unsuccessful attempt during the testing. Some factors that influence the performance of micro quadcopter include an overheating processor unit and heat sensor that prevents the estimated value to appropriately being checked. In conclusion, the advantages of using a micro quadcopter for odor source localization include increased flexibility and agility, faster scanning, and not limited by terrestrial topography. The search technique is based on the behavior of the search spiral, which is a promising rate of 70%. The localizing procedure is also considered a success for the micro quadcopter because the average time spent to locating the odor is just 24.57 seconds. As a result of this conclusion, the micro quadcopter equipped with the proposed silk mod with search spiral approach and Savitsky-Golay filter has completed the search for the odor source in the low computational controller. For future works, the proposed method, the search spiral algorithm, and the Savitsky-Golay filter in 3D spatial position will be evaluated by altering the odor source. That will be all from my presentation. Thank you for your attention.